Calculating the magnetic field around a perfectly straight wire is mathematically straightforward, but in reality, engineers and physicists rarely deal with such idealized lines. They work with coiled solenoids, twisted plasma streams, and intricate circuit traces, complex geometries defying textbook equations. To solve for these systems, we must move past the macroscopic view and isolate a single infinitesimal slice of the conductor. This highlighted microscopic segment is the current element. It is the fundamental building block used to construct any magnetic field. To understand the whole, we first calculate the precise magnetic field this one tiny slice generates at a specific point in surrounding space. This specific microinteraction is defined by the Biot Savart law. We will construct this law from the ground up, starting with basic scalar geometry and upgrading it into a full three-dimensional vector framework applicable across all physical dimensions. Reducing complex systems into differential elements provides the necessary mathematical framework for mapping real-world field topologies. In this physical setup, we have a curved wire and an isolated current element, denoted as IDL. Our goal is to find the magnetic field it creates at point P, located at a distance defined by the position vector r. The magnitude of this differential magnetic field, dB, scales directly with the total current, I, and the physical length of the element, dl. As the distance increases, the field strength drops. It follows an inverse square law, scaling proportional to 1 over r squared. We must also account for the geometry of the observation. The field strength depends on the sine of theta, the angle between the current element and the observation point. Combining these four observations yields a unified scalar expression for the magnitude of the differential magnetic field. To turn this proportionality into an exact equation, we introduce a balancing constant, μ0 over 4 pi. μ0 is the permeability of free space, a constant valued at 10 to the negative 7 Tesla meters per ampere, dictating how magnetic fields propagate. While this equation calculates the raw strength of the field at point P, it lacks the spatial orientation required to describe how fields behave in 3 dimensions. Because magnetic fields are directional entities, the scalar model is incomplete. We must shift the model into vector mechanics. This spatial orientation is governed by the right-hand thumb rule. When the thumb points with the current, the curling fingers map the geometry of the resulting magnetic field. The relationship is strictly perpendicular. These magnetic field loops are orthogonal to the current flow. In vector algebra, an operation that produces an orthogonal result and scales with a sine angle is defined as a cross product. This gives us the formalized vector equation of the Biot Savart law. The scalar sine term is replaced by the cross product of the current element and the position vector. You'll notice the denominator is now r cubed, which appears to contradict the inverse square law. This is a matter of vector normalization. Because the cross product uses the full position vector r, which has its own length, we divide by an extra r in the denominator to keep the physics balanced. Mathematically, r over r cubed simplifies back to 1 over r squared, maintaining the inverse square relationship. This powerful cross-product formulation encodes both the physical magnitude variations and the orthogonal spatial geometry into a single, highly efficient mathematical operation. We can verify this vector model by testing boundary conditions. Here, we map 2 observation points, P and Q, sitting directly on the axis of the current flow. At point P, the observation is directly ahead of the flow, making the angle theta 0 degrees. At point Q, the observation is directly behind the flow, yielding an angle of 180 degrees. The sine of both 0 and 180 is 0. Consequently, the cross product and the resulting magnetic field vanish at these points. Physically, this means a segment of moving charge generates no magnetic field along its own trajectory. Since the field strength only reaches its maximum at 90 degrees, the field topology forms a torus rather than a sphere. Recognizing this axial blind spot is essential when integrating complex 3D structures, as it identifies regions where calculations are unnecessary. The Biot Savart architecture remains consistent whether we are looking at macroscopic conductors or microscopic subatomic particles. To model a 3D volume, such as a plasma stream or metal block, we replace the linear current with J, the volume current density. Through algebraic substitution, the one-dimensional line element morphs into a three-dimensional volume element. The core structure of the volume formulation remains identical. simply swapping the line element for the density cross product. We can shift focus further to the microscopic limit, stripping away the wire to look at a single isolated particle. Here, the current element is represented by a single charge, Q, moving with a velocity vector, v. This point charge equation shows that the cross product of velocity and position dictates the field, just as it did for the macroscopic wire. From massive plasma volumes to individual electrons, the geometric architecture connecting motion to magnetic fields remains invariant. Placing these manifestations side by side reveals their shared mathematical structure. The cross-product engine is the constant across every scale. Biot Savart provides the geometric bridge that connects moving charge to magnetic reality. Solving the complexity of microengineering begins with mastering this micro-interaction. By understanding how a differential element projects its field into space, we can map the magnetic topology of any system in the universe. Vector geometry natively encodes the precise mechanical behaviors of electromagnetism across all dimensions.